Hello, this is Trevor from Telecom Training, and today we're going to be talking about how telecommunications companies use single mode fiber optic cable to get their voice over IP, high-speed internet data, and IPTV signals from the central office to the subscriber's premises. Now here we have voice over IP and high-speed internet data signals. We're going to be talking about the IPTV signal later because that is processed a bit differently in the way it is sent from the central office to the subscriber's premises. So your voice over IP and high-speed internet data is sent into the router using an Ethernet cable, and then this signal is sent from the router to an OLT using another Ethernet cable. Now the OLT stands for Optical Line Terminal. The purpose of the OLT is to convert your voice over IP and your high-speed internet data from an electrical signal to an optical signal. And it uses 1490 nanometers as the carrier signal, taking both your voice over IP and your high-speed internet data down the fiber optic cable to the CSP. CSP stands for Central Splitting Point. You may have a splitter with 16, 32, or 64 lines going to different customers. The most popular one is 32. So you would have 32 single mode fiber optic cables fused to the fiber optic cable coming from the central office. Now the same data on each one of these fiber optic cables going to individual customers will be here. So in other words, if there are 32 customers data on this line, there'll be 32 customers data on each and every one of these fiber optic cables. Obviously that's a security issue right there. So we're going to be talking about how this all works so that this security issue does not exist. Okay, so from here these cables can be connected underground going to the customer, or it can be connected by a pole. In this particular example, we have it going to a pole. We have a line going from the CSP to a pole. At the pole here, we have a terminal where the drop wire from the terminal is connected to the customer's premises. At the customer premise, an ONT, which stands for Optical Network Terminal. The purpose of the ONT is to convert your signal on the fiber optic cable from an optical signal back to an electrical signal so that you can power your telephones and your modems, etc. Okay? Now, the first thing a technician would do before plugging his fiber optic cable into the ONT is to check that cable to see what the level of light is on the cable. That would be the optical signal level, 1490 nanometers. It was sent from the OLT at 0 dB. But normally by the time it gets to a subscriber, it will be somewhere between -14 dB and -18 dB. The reason for this great loss is because of the splitter. The maximum distance a fiber optic cable can go using the CSP is 20 kilometers. Now, the maximum distance for a fiber cable without a CSP is 100 kilometers. So you can see how much loss actually happens here. So once this level is fine, you'll go ahead and connect your cable. If it is not, you probably want to check your connection points like here at the pole and also here at the CSP, because these connections are very sensitive to dust. One speck of dust can actually disable the entire line because the area in the fiber optic cable where that light is traveling is extremely small. So one speck of dust can actually stop it from working completely. So you want these connections to be dust free. Once everything is fine, the next thing you do before you connect your ONT would be your encryption. Remember, as I said back here, is that you have 32 customers on this line, for instance, okay? And you have 32 customers on each and every one of these because there's no filtering in here. So the same thing that you will have on this line, you will have on each and every one of them. So you have 32 customers on each one of the fiber cables going to the customer. So you have to find a way to secure each line where each customer is not receiving each other's data. All right, so we're going to talk about that on the next screen. Now here we have 3 different customers connected on this line. One using an underground cable, just to show you how that is done, and also the others using a cable which is connected to poles. Now this is what a CSP would look like from the street. As I said before, the data for all 32 customers would be on each one of these customers' line. So to prevent these customers from getting each other's data, we use an encryption key. This is a key here that I'm going to be using, 110J5, 110H5, 110D5. Now these encryption keys are usually much longer than that, but I'm just using a short key just as an example to show you exactly how this works. As I said in the last slide, each of these ONTs have a unique encryption key built in. Of course, these encryption keys in the real world are much longer than these ones. I'm just using these short encryption keys for simplicity. But each one of these ONTs would have a unique encryption key built in. Now, data sent from the OLT to the ONT are sent within Ethernet frames. This includes the source IP and the destination IP. But what we're going to talk about right now is the encryption key, which is on the end here. Each frame that is sent has a unique encryption key, and this encryption key would be an encryption key of a particular ONT. Now, frame 1 here is the encryption key of ONT 1 with this 110H5. Frame 2 is the encryption key of ONT 2, and frame 3, which we have 2 of them, has the encryption key of ONT 3, and we have another frame here for ONT number 2, which would also have this encryption key. Now these ONTs would only accept the frames that has its unique encryption key. So frame 1 here would have a unique encryption key for ONT 1. So ONT 1 would only accept frames that has its unique encryption key. So this is how the security is done. This ONT would ignore all of the other frames except for the ones that has its unique encryption key. Now so far we've been talking about data coming from the central office to the customer. But what about data going from the customer back to the central office? Like when you're speaking on the phone, or when you are trying to get onto a website, or you're uploading data from the customer's frame back to the central office. We have to have a way to do that as well. So the way this is done is with time division multiplexing. And we use a wavelength of 1310 nanometers for upstream. With single mode fiber cable, physically you cannot have more than one light wave on the line at a time. But we need to send data upstream, but we can't have the bandwidth downstream at the same time. So what happens is that when these ONTs have data to send back upstream, this OLT will just briefly stop the transmission of this 1490 nanometers. And then these ONTs would be allowed to send data at 1310 nanometers upstream. But they all gotta have a system of sending that data. They just can't send it all at the same time. They send it using time division multiplexing. Now each one of these ONTs are given a time slot. Like ONT 1 give time slot 1, ONT 2 give time slot 2, and ONT 3 give time slot 3. This is how data is sent from the ONT back to the OLT, and this is done in a burst. Like this 1490 nanometers stop, and then there's a burst of data with all the ONTs sending on the different time slots within that specific time, and then 1490 nanometers we put right back on the line sending. And then again, when these ONTs have data, to send back up to the OLT, the OLT would briefly stop the 1490 nanometers transmission downstream and allow these ONTs to send the 1310 nanometers, each of them sending back. This entire system that we've been talking about is called a GPON. GPON stands for Gigabit Passive Optical Network. Now gigabit, because of the speed, the earliest speed that we have gotten in this network was 2.4 gigabits per second, down by 1.2 gigabits per second up. Now that was later upgraded to 10 gigabits per second, down by 10 gigabits per second up. And this speed will continue to be upgraded as higher speeds are required. Now, in order to upgrade the speed, there's no need to upgrade your fiber cables. The fiber cables are capable of carrying speeds much higher than the 10 gigabits per second that we're using today. The only changes that will have to be made where upgrades are concerned would be the OLT, the router, and the ONT at the customer's premises. Now the second word we have in that name is passive. When they talk about passive, they are referring to the splitter. The splitter has no power connected to it, no electrical power. All you have is a light signal going in, and this signal is being split among 32 other subscribers in this case. There's no power, so that's how we get the name passive. Optical, that's because it's light. There's a light signal, so that's how we got the name optical. So as I said before, this is called a Gigabit Passive Optical Network. Now next we're going to be talking about IPTV. Okay, so far we've talked about voice over IP and internet data. We talked about the fact that we use 1490 nanometers to get it from the central office to the customer's premises. Now we want to send IPTV as well. And IPTV requires more bandwidth than is available on 1490 nanometers carrying voice over IP and internet data. We actually require a separate wavelength for video because of the high bandwidth requirements. So ISPs choose to use 1550 nanometers for video. Now the problem with single mode fiber is that we can only send one wavelength at a time. We can't send 1490 and 1550. So it's either we send voice over IP and internet data, or we send TV, but we can't send both on this fiber optic cable. The other choice you can have is ISPs will have to run a brand new fiber cable to every neighborhood, which will be very expensive because it would be involved digging up the street again, running cables. It would make the service much more expensive, much less affordable for customers. So that was not really an option for ISPs, but they had to solve this problem. So what they did is that they incorporated a multiplexer within the OLT. The purpose of the multiplex is to merge both the 1490 nanometers and the 1550 nanometers being used for video together within this multiplexer. This signal, once multiplexed, is sent out onto the single mode fiber optic cable as one light source carrying both wavelengths. Now this multiplex signal goes through to all the ONTs. Now let's talk about ONT number one. What's happened with ONT number one? First of all, these two frames here is going to ONT number one. One has 1550 nanometers, the other one has 1490. They both have the encryption key for ONT number one. So when this signal gets to ONT number one first have to demultiplex the signal. Once demultiplex, the ONT will be able to see the frames within that signal, and it will see that it has 1550 and 1490, and there's an encryption key in both frames that matches the encryption key within this ONT. Then the ONT will convert the 1550 from an optical signal to an electrical signal and send that signal off to the television. And for 1490 nanometers, once this key is the same as the key in the ONT, then the ONT will convert that signal from an optical signal to an electrical signal and send it off to the modem and the phone service as well. What you'll notice here for ONT number 2, they only have a 1550 nanometer frame. There's no 1490 nanometer frame. So once your signal gets to ONT number 2, first it is demultiplex, and once demultiplex, the ONT would be able to see that there are no frames coming to that ONT with this encryption key in the 1490 nanometer area. So it would reject all frames within the 1490 nanometer area. In 1550 area, it will see that the keys, the encryption keys, are the same. So it would then convert the 1550 nanometer signal from an optical signal to an electrical signal and send it off to the TV. So this customer here wouldn't have any phone and they would not have any internet, but they'll have TV service. ISPs do provide a modem and enough bandwidth to run the TV even though you don't have an internet service. This bandwidth will be dedicated to the TV only, but not where you can plug in your computers and have internet service as well. Now for ONT number 3, you'll notice that there's a frame here at 1490 nanometers for this customer, but there's none at 1550 nanometers. So this customer here would receive the signal, demultiplex it, and then this ONT would be able to see that there are frames at 1490 nanometers with its encryption key. It will convert this frame at 1490 nanometers from an optical signal to an electrical signal and send it off to the modem and also the phone service. So this customer will have phone service and internet service, but no TV service, because it would reject, this modem would reject all frames coming in at 1550 because the encryption keys do not match for the 1550 wavelength. Let's say there weren't any encryption key within an ONT. It would simply mean that if there's no encryption key in the ONT, all the data, both at 1550 nanometers and 1490 nanometers, will be rejected by the ONT. So the ONT, it receives the data, it demultiplexes it to see what's inside, and once it demultiplexes it, it will be able to see the 1550 and 1490 nanometer frames, but it will not be able to find a frame with an encryption key that matches the encryption key in here, because obviously there's no encryption key. So all the data for both 1490 and 1550 would be rejected. This is how telecommunications companies use single mode fiber optic cables to send voice over IP, internet, and IPTV signals from the central office to the subscriber's premises. I hope this video has been helpful to you, and if you haven't done so as yet, please don't forget to click on the subscribe button below so that you'll be alerted as soon as our new videos are released. My name is Trevor from Telecom Training. Thank you for watching.